So here's another 6.6 or 6.6 calculation. And what this one says is calculate the final temperature after adding 6.8 grams of aluminum. And here's our heat capacity for aluminum at 67.4 degrees Celsius in 195 degrees of water at 19.6 degrees Celsius. So what we need to do is we need to say what we know. 0 is equal to the the mass of our water times the heat capacity of water times our delta T of water. Now we don't know the delta T of our water because we don't know the final temperature. That's what we're trying to figure out. So essentially what this means is we are setting up an equation that equals 0 of mass of our water is 195 grams. Heat capacity of our water is 4.184 joules per gram degree Celsius, and then T sub F minus 19.6. Okay, all of this is added to, well, here we've got mass of our aluminum, 6.80 grams. We have the heat capacity of our aluminum, 0.892, and our delta T for this is going to be a little bit different because of the fact that, well, we know our initial temperature of our aluminum, but we don't know our final temperature of aluminum. So that would be T delta or T sub F minus 67.4. Now what I want to do is subtract all of this over here. So I'm going to set this as negative 6.80 times 0.892 times T minus 67.4 is equal to 195 times 4.184 times T sub F minus 19.6. Okay, so what I will do with all of this is basically do as much multiplication as I can. So I'm going to say 6.80 times 0.892 is equal to 6.0656 multiplied by T negative 67.4. And this is still a negative out here. So then I will get negative 6.0656, and that will be, I'll distribute this, so there, that will be plus, so 6.0, yeah, that's T sub F, plus times, or sorry, added to, let me erase this real quick so it's a little bit more clear. So I multiplied this negative 6.0656 times T sub F. Now I'm going to multiply it by negative 67.4. And that's going to be plus, because those two negatives will cancel out, plus 408.82. That is equal to 195 times 4.184, 815.88. So I multiplied these two by one another, and now I'm multiplying that by T delta or T sub F minus, and so this is 815.88 times 19.6 minus 15,991.248. Okay, so now what I will do is add this 15,991.248 plus 408.82 equals, I've got, and then I will just add the 6, so I've got 16,400.068. So I got this off this side. I combined it with this 408. Now I'm going to add, to get this negative over to the other side, I'm going to add 6.0656 T sub F to this right here. 0656 T sub F So that will be 815.88 plus 6.0656 equals 821. So now I'm going to go ahead and get it a little bit more organized. I'm going to say 16,400.068 is equal to 821.9456 T sub F divide by 821. 9456 divide by 821.9456, so 16,400.068 divided by 821.9456 equals 19.952 equals T sub F. So my final temperature, I'm going to go ahead and adjust that down to 20 degrees Celsius. So there's a little bit involved in that calculation, but there it is. Now, the next thing that I want to talk about, and I'm just going to do this fairly briefly, is constant pressure calorimetry. Constant pressure calorimetry is commonly carried out in undergraduate labs. This semester, what we're doing is we're using, if you're taking Chem 1141, we have an exercise where you basically watch this sort of thing take place using a styrofoam cup. The reason that you use a styrofoam cup in this constant pressure calorimetry type of experiment is because it's insulated, so that styrofoam doesn't lose any heat. Just like whenever you're drinking coffee from a styrofoam cup, your hand doesn't get warm. So this minimizes heat transfer between the system and its surroundings. The system is not sealed, so the calorimeter pressure is the atmospheric pressure. This type of system makes it easy to measure Q sub P for any heat transfer that can happen in an aqueous solution. So for chemical reactions, Q sub P is your delta H, the enthalpy change for the reaction. So this is what that kind of looks like. You've got this lid, but it's not sealed tight. You've got a pair of styrofoam cups to basically double the insulation. And you're also going to have a magnetic stir bar so that your solution can be mixed up. So for the process happening in the solution, Q sub solution is equal to negative Q sub P. The release or absorption of heat that occurs when a solid compound dissolves in a solvent at constant pressure to infinite dilution is known as enthalpy of solution, or delta H sub solution, or heat of solution. Both reaction enthalpies and heats of solution are commonly measured using constant pressure calorimetry. So this is just kind of illustrating the technique, so how you can actually observe a reaction taking place. You see the temperature change, you know the mass of the water, the mass of the substance can potentially be negligible. It's generally going to be negligible, so you can see the formation of that solution and determine the heat associated with it. Well, that's all that I've got for this section 6.6 or 6-6. I hope this is helpful, and I'll see you in 6.7 or 6-7. Have a good one.